Welcome to my YouTube channel Mechanical Magic Mechanical Learning Tutorials. So in this video I am interested to talking about Otto cycles. So basically Nicholas-A-Otto, a German engineer, developed a first engine on this cycle in 1876. So that will be the first invention of Otto cycle, and that will be run on one engine. So basically in that, air is used as a working substance is known as air standard efficiency. So in the case of Otto cycle, or you can say for deriving or analysis of air standard cycle efficiency, some of the assumptions as under, and that will be working fluid is air. In cycle, all the processes are reversible. If air is a working substance, so that will be behaving like a perfect gas over here. So that will be having a specific heat at constant pressure. So that the value of Cp for air, and that will be 1.005 kilojoule per kg Kelvin, and specific heat at constant volume, and that should be 0.718 kilojoule per kg Kelvin, and a gamma, that will be Cp upon Cv, the relation, and it should be 1.4. Some more assumptions of this theory, and that will be mass of a working fluid remains constant through entire cycle. And last one, heat is supplied from constant high temperature heat reservoir and some heat rejected from the fluid to the sink. So basically heat supplied from the high temperature reservoir, and that should be supplied after the work done to the sink, and that will be having a low temperatures. So in that case basically four processes going that. So let us see with some of the examples over here. So let's see the one of the piston cylinder mechanism over here. So here just you can see the container, that will be the insulators like this, and here the valves. Just you can see over here, that will be the piston inside of the cylinders. That will be the one more positions of the piston. So up to this, just you can see from the diagram, so that much area it will be considering as a total volume that will be inside the cylinder, and from here that will be the clearance providing into the cylinder. So clearance volume, and remaining portion that will be piston has to move, that will be called as a swept volume. So let us see onto the PV diagram of same example. So here P, V, and as from the initial position over here, so that will be 1 number point. So basically adiabatically, or you can say isentropically, compression. So 1 to 2 process, or you can say state number 1 to 2, that will be, so pressure and temperature is being increasing, so that will be having a P1 pressure, and it should be increasing with P2 2 from here, and Otto cycle, so that will be, you can also say, constant volume heat addition. So at constant volume, or you can say 2 to through heat addition process, so that will be the point number 3, and that will be increasing pressure and temperature once again up to the point number 3. So heat addition, that means Q supply over here. So that will be the process 2 to 3. After 3 point, or you can say state number 3, due to the expansion, you can say isentropically expansion up to the 4 number point, or you can say adiabatic expansion in the representation PV raised to gamma equal to constant. So from 3 to 4 process, pressure and temperature, that will be reduced, so that will be the P4. And once again 4 to 1 process, you can say expansion process, or you can say constant volume expansion process. So during that, heat rejection to the 1. So 4 to 1, that will be the heat rejection process. So you can see that once again that will be at the pressure P1, and cycle it will be completed over here. So that will be the Otto cycle, or you can say constant volume heat addition cycle. So now we will see the efficiency of an Otto cycle. So here heat supplied that will be Qs equal to M into Cv during T3 minus T2 process, and heat rejected, and that will be Qr equal to mCv T4 minus T1. So that will be the two important formulas for heat supply and heat rejected. So now net work done, so W net, that will be equal to Qs minus Qr. And one more thing, air standard efficiency, and that will be efficiency equal to net work done divided by heat supplied. So from here, net work done, that means Q supply minus Q rejected, so Qs Qr divided by Qs. So simply put the value of Qs and Qr from equation number A, mCv T3 minus T2 minus mCv T4 minus T1 divided by mCv T3 minus T2. So from here, mCv, that will be, and T3 minus T2, that will be common out and cancel. So 1 minus T4 T1 divided by T3 minus T2. But over here total volume from the figure, and that will be V is equal to Vc plus Vs, that is the clearance volume plus swept volume. So from that figure, Vc equal to V2. So just you can see from the compression ratio that will be representing as a R. So V1 upon V2. For the next process, R is equal to V4 upon V3. So that will be the two compression ratios in the case of Otto cycles. So from figure, V4 equal to V1 and V3 equal to V2. So from process 1 to 2, and that will be T2 upon T1, that will be equal to V1 upon V2 raised to gamma minus 1, and that will be equal to R raised to gamma minus 1. And similarly for process 3 to 4, so T3 upon T4, that will be equal to V4 upon V3 raised to gamma minus 1. So similarly 1 minus gamma minus 1. So just put the value of T3 and T4, or you can say T4 and T1. So from equation B, efficiency equal to 1 minus, so T4, so that will be T3 divided by R raised to gamma minus 1 from here. So just you can equate it with the T4 and put the value into these equations. Minus T1, so T2 divided by R raised to gamma minus 1 and whole divided by T3 minus T2. So that will be common and cancel out T3 minus T2. So finally you will get 1 minus 1 upon R raised to gamma minus 1. So that will be the efficiency of an Otto cycle. So basically for Otto cycle, the compression ratio, you can say R in between 6 to 10 is being used. So thank you so much. If you understand, like, then subscribe and share. Mechanical Magic, Mechanical Learning Tutorials.